Hey guys, this is section 2.2 and we'll dip into section 2.3, but it's pretty much learning your differentiation formulas, okay? Here's your FLT. Pause and play when you're ready. Given a function, I will be able to find the derivative by using the differentiation formulas. Okay, so you're learning a lot of different techniques throughout the next few lessons, but remember, as I said in the previous lesson, don't lose the meaning behind what a derivative is, okay, and what it represents, all right? So here we go. Let's revisit something, okay? Let's say I had f of x equals 2x plus 1. What I want you guys to do right now is I want you to find the derivative, okay? Pause and play when you're ready. So the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so that's going to be the limit of 2 times x plus h plus 1. That's this right here. Minus 2x plus 1. And that is this right here. All over h as h goes to 0. Okay, hopefully you guys have had enough practice there. But let's keep going. The limit as h approaches 0. Okay, up top, if I distribute, I'll have 2x plus 2h plus 1 minus 2x minus 1 if I distribute that negative all over h. I notice that 2x minus 2x goes away along with plus 1 and minus 1. I'm left with 2h over h. And I didn't take the limit yet, so I'm going to bring it down. So I notice that you could actually divide by an h there, so you're just going to be left with 2, which is odd, right? By odd, I mean strange. So when h goes to 0, you still are left with 2. Now here's my question to you guys. What does that represent? Okay, pause and play when you're ready. Okay, so hopefully you guys said something along the lines of the slope of the tangent line or the instantaneous rate of change. So a follow-up question, is this the general slope or is this the specific slope? Pause and play when you're ready. Now this one is a little bit tricky because it's actually both the general slope and the specific slope. Because for some reason, we ended up with just a constant and no variables next to it. What this tells us is that the slope will always be 2. Now think about that. Just so that you guys can make some connections here. What does that look like graphically? What does the function look like graphically, right? You should understand that 2x plus 1 is just a linear function. It looks something maybe a little bit like this, right? And you guys got to remember, with a line, can't you guys find the slope, right? Isn't that just rise over run? Isn't that just this little guy right here from y equals mx plus v? Okay, so the thing is, although you could use calculus to find it, anything that's linear shouldn't require calculus. Okay, you could just look at this coefficient in the front. That tells you that the slope is 2. Okay, so just keep that in mind. And here's a question. If derivative means slope, right? What if your function, here's a separate problem now, is f of x equals 7. Okay, now, do you know what that graph looks like before we move on? Okay, and if you don't, go ahead and graph it on your calculator or on Desmos or whatever device you're using. Okay, you should know that when a function is just a constant, you'll have a horizontal line at 7 That's f of x right there. Okay? So here's my question to you. Without doing all of this calculus right here, tell me what f prime of x is. Okay? Pause and play when you're ready. Okay, so without doing all of that, all the calculus, remember derivative means slope. The slope of that line right there, it's a horizontal line, so we know that the slope is going to be 0. Logically, right? So, here's a follow-up question for you guys. If the f of x was 5, what is the derivative? Okay. Hopefully you guys said 0. If f of x was negative 6, what's the derivative? Okay. 0 as well. So look, we've uncovered something here. What if f of x was any constant c? What would the derivative be? Right? So this is called your constant rule. Okay? If you take the derivative of any constant, it will come out to 0, which is basically this right here. Now, the way you read this, when they put a d over dx next to something, they're saying that they're taking the derivative of it. Okay, so the derivative of c with respect to x, okay, is going to be 0. That's your first rule if you want to call it a rule, but it's very logical, okay? If you understand derivatives mean slope, then you guys should understand that the slope of any constant line has to be 0, okay? So the more sense that you can make of every rule, it becomes less and less of a rule, okay? And something that's more natural for you to understand. Okay, so here's what I did for you guys, okay? I used the limit definition of a derivative. This right here, this is what you guys did in the last assignment for these 3 functions. Okay, I did all the work and then I wrote out my general slope for every derivative there. Okay? If only there was some way to kind of figure out a shortcut or a pattern to this, right? So take a look at these. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the 4th is 4x cubed. Do you notice any patterns? Okay, pause here. It's not too transparent, but try to just think about it. Pause there and play when you're ready. Okay. If you do see a pattern, okay, now you don't have to say out the pattern. Okay, let's just see if your pattern works. I'm going to ask you to find the derivative with respect to x for x to the 10th power. Okay, pause and play there. Guess what that answer is and see if it matches up with mine. Okay, so whatever your pattern is, it should work for this one. The derivative of x to the 10th is actually 10x to the 9th power. Okay? Now, if you got the answer right, that means you're probably onto something here. All right? Let's do another one. And if you don't see it yet, you will. The derivative of x to the 99th power. Okay? Pause and play when you're ready. The derivative of x to the 99th power will be 99 x to the 98th power. Okay, let's do one more just to make it sure. Let's do x to the 1000th power. Okay, pause and play when you're ready. The derivative of x to the 1000th power is 1000 x to the 99th power. Okay, so by now, I'm sure most of you have figured out a pattern. So isn't this way faster than using the limit definition of a derivative? Sure is, right? You don't have to do the limit of f of x plus h minus f of x all over h. cancel out a bunch, reduce the h, take the limit. There's a lot of work there. So there's a neat little shortcut here. So what is that shortcut, right? Here it is. This is called the power rule. Okay? When you take the derivative of any polynomial, meaning x to the some number, okay? You take that old power, okay? The base stays the same, x, and then the new power is going to be 1 less, right? So for instance, we had the derivative of x to the 1,000. So if your n is 1,000, the 1,000 goes in the front, the base x stays the same, and your new power is going to be 1,000 minus 1, which is 999. Pretty neat, right? So we're figuring out faster ways of finding the derivative without having to do that extensive limit definition, okay? So remember, you guys are learning all these rules, but remember, a derivative means what? It means the slope of a tangent line, right? The instantaneous rate of change. How fast something is changing at one particular moment, okay? The slope of a tangent line. I think I said that already. Okay, here we go. Here's some for us to try. Here's example 1. Write out part A. Play when you're ready. Okay, so here I actually want you guys to write out all the directions, okay? So that you're familiar that they could write it in many different ways, but it means really the same thing. If f of x is x to the 6, then the derivative f prime of x, make sure you guys know how to read it, okay? F prime of x is equal to, pause and play when you're ready, 6x to the 5th power. All right, cool. Here's part B. Go ahead and write part B down. We already did this one. Cool. So if y equals x to the 1,000, then y prime, okay, that's a little prime symbol. It's kind of stuck with the y there. And y prime will equal 1,000 x to the 999 power. Okay, here's part C. Now, notice the notation that they used. If y equals t to the 4th, then dy over dt. That just means the derivative of y with respect to t. But you guys could just say dy over dt. Okay? So that's pretty much saying that if t is your variable, okay, what's a derivative? That's just going to be 4t to the 3rd power. Okay, please text me if you guys have questions, okay? Now here, notice how they didn't explicitly write out the functions like they did up here, where f of x is x to the 6, y is x to the 1,000, y is t to the 4th. Here, the function is already given in there, so it's a different way of writing it. So the derivative of r cubed with respect to r, so that's pretty much saying that r is a variable. That's going to be 3r squared. Cool? Okay, not that bad. It does get a little tricky, so I'm going to show you all the different ways that they could possibly try to fool you. So we're going to do a couple more. Here's part E. Just write out part E for now. Pause and play when you're ready. If y is x to the 2/3 power, then y prime equals, I want you guys to just try this one, okay? And then play when you're ready. Okay, so even though your exponent is a fraction, it still has to follow the power rule, all right? So the rule is you bring that power down, okay? That base will stay the same, and that new power is going to be, and that new power is going to be 2/3, but 1 less, right? So sidebar, 2/3 minus 1, we're going to need common denominators. So that's actually going to be 2 minus 3 all over 3, which is negative 1/3. Okay, don't worry about speed there. Just take your time. So this is really 2/3 x to the negative 1/3. All right, it's not the cleanest answer, but you still got the job done. All right, so don't let fractions freak you out. Now, furthermore, suppose this was a multiple choice question, right? You might not see this as an answer. Usually what they do is they try to fix your negative exponents, okay? So just remember, whenever you have a negative exponent, it goes down to the denominator in general, okay? So this right here is really, here's a quick recap. If you have something like x to the negative 2, that's the same thing as 1 over x squared. All right? So here I have 2/3. So x to the negative 1/3, since it's a negative exponent, I know it's going to go down below. Okay? You might even see it like this. So I'm writing all possible ways. Remember that x to the 1/3 power is really just the cube root. My main concern is you guys knowing how to get here. All these little bits here, I could always catch you up on in case you're not familiar with that, okay? It's just a way of rewriting it. Okay, so go ahead and write down part F. Okay, so here part F of x is the square root of x, and we want to find the derivative, just the general slope. You guys have to remember that you can rewrite roots as fractional exponents. So what you don't see here is that invisible 1 right here, and that invisible index right here is a 2. All right, and it's always power over index, power up over index. So the square root of x is really the same thing, and I'll write it down here. F of x is equal to x to the 1/2 because the power is 1 and the index is 2. So if we go back to this one here, x to the 1/3, the power is 1, the index is 3, which is why I wrote it like this. So you guys have to be comfortable eventually. It's okay if you're not now, but comfortable eventually to rewriting it in case you don't see your answer. All right? So here's the thing. Notice how I didn't write x to the 1/2 right here. Can you guys think of a reason why I didn't do that? Pause and play when you're ready. I didn't do that because x to the 1/2 is not the derivative. Okay? AP readers, when they look at your exam, they want precision. So don't say that the derivative is x to the 1/2 because it's not. X to the 1/2 is just a rewritten version of f of x. All right? So just keep that in mind. And I'll be picky with that when I look at your assessments, okay? So knowing that f of x is x to the 1/2, go ahead and find the derivative there. Pause and play when you're ready. Okay, so power rule, we're going to bring the 1/2 down. X stays the same. The top is going to be 1/2 minus 1. But 1/2 minus 1, you guys could do it on the sidebar here. We're going to have to get common denominators. You're going to eventually end up with negative 1/2. So I'm just going to jump to that. You don't have to write every single step, but don't try to rush it if you don't see it. Okay? So write it at your discretion, I guess. Okay? Now, we're pretty much done here, but for the sake of equivalence, okay? Can you guys write out 2 other ways that the answer might look like here, okay? How could you manipulate this so that it looks a little bit different? Okay, pause and play when you're ready. This could be written as 1 over 2x to the 1/2 because of the negative exponent, or I know that x to the 1/2 is the same thing as the square root of x. All right, cool. Here's part G. If y equals 1 over x cubed, then dy over dx equals. So remember, dy over dx is just derivative, okay? Now here, the thing is, 1 over x cubed does not look like x to the n power. So we cannot use the power rule. So we have to rewrite this in a way where it does look like the power rule. Kind of like in part F, right? We had a square root that does not look like x to the n, so we had to rewrite it here. Okay? So here's a little recap. Kind of like the same reasoning. Remember how x to the negative 2 is the same thing as 1 over x squared? Well, we're just going backwards here. If you have 1 over x cubed, that's the same thing as x to the negative 3. Okay, so this is how everything connects from all the way back to Algebra 1 or IM1. You got to rewrite it so that you're able to use the power rule, all right? So now that it looks like x to the some power, the derivative is going to be, pause and play when you're ready. It'll be negative 3 x to the negative 3 minus 1. Okay, it's always 1 less. So what's negative 3 minus 1? That's negative 4. Okay, if you put negative 2, you got to be careful. All right, it's always 1 less. 1 less means you subtract 1. Okay, now how else might this answer look like? Okay, so x is being raised to the negative 4th power, so I know that x is going to go down below to the 4th power. Now, negative 3 does not have a negative exponent, so negative 3 has to stay where it is. Okay, oftentimes I see students do this. Okay, that negative 3 does not have a negative exponent here. The only thing being raised to the negative 4th power is that x. Now, if it was written like this, where everything was raised to negative 4th power, then yes, you would bring that entire quantity down. So really what you guys are doing here is you're learning like a tiny bit of calculus, but you're really revisiting all that algebra that you learned or may not have learned so well, right? But that's the cool thing about calculus. This is where you get really good at your algebra, okay? Cool. Now, here's the next, I don't want to call it a rule, but I mean, for the sake of notes, this is your constant multiple rule. It's really logical here, okay? So here's your rule. I'll explain it through an example. Let's say we wanted to find the derivative of 8x cubed, right? Okay, now this is a little bit different because there's that 8 in front of it, that constant multiple. Really, it should be called a coefficient, but whatever. That's just Mr. Lee ranting. That constant, what you do is you just ignore it. Okay, you leave it to the side, and really what you're doing is you're taking the derivative of the main course, the meat. Okay, so you ignore that 8. So then the 8 we're just going to bring down. What's the derivative of x cubed? That's going to be 3x squared. And then you bring that 8 back in. Okay, 8 times 3 I know is 24. X squared, and that's it. It's called a rule, but it's really intuitive. Okay, you ignore the constant or the coefficient, and then you bring it back later. So let's try a few. Here's example 2. Okay, here's part A. Write it down. Okay, now I'm writing it out in steps. Eventually, you guys are going to find your shortcuts, okay? So we have a constant multiple of 3 here. We're just going to scoot that 3 to the side, and we'll just take the derivative of x to the 4th. Okay, x to the 4th, the derivative is going to be 4x cubed. And then I bring that guy down. Don't forget to bring him down. Okay, so if I smush this together, I should get 12x cubed, and that's it. Constant multiples, not that bad. Don't think of it as a rule. Just push it to the side, bring it back later. All right. Now, this one here, people tend to you know what? Do this problem here, okay? Pause and play when you're ready, when you have an answer, okay? Okay, so some people will notice that there's a negative in the front, which is a -1. So they scoot the -1 to the side, and then they take the derivative of x. And then they do like the derivative of x to the first power is 1x to the 0. Okay? And you're right, okay? But don't forget x to the 0 power. Any non-zero number to the 0 power will always be 1. That's the 0 exponent rule. So really, you're just left with -1 times 1, which is -1. Okay? Now, if you did this, it's okay. I'm not there to shame you. But take a look. Oftentimes, we lose context. Okay? We're so caught up with the algebra or the analytical piece here. Think about what this really means, you guys. What are you really finding? You're finding the slope of that. But -x is this right here. And with the line, can't you find the slope an easier way? Isn't the slope of the equation of a line y equals mx plus b? Right? So m here is your slope. So m is really -1. Okay? Now, if you didn't see that, that's okay. That's what I'm training you guys to do. So don't feel bad if you didn't see it that way. I'm just getting you guys to never forget. Okay, don't forget what that meaning is. Oftentimes in math, in lower division math, like you guys do all these tricks, but then you don't remember the meaning behind it. And if you don't understand that, then what's the point, right? So I'm training you guys to do that. Don't lose the context. Slope of a tangent line, the instantaneous rate of change, okay? All right. Here's the sum rule, okay? It looks complicated, but it's not. So write it down first, and then I'll explain it in a very easy way. Okay, so here we have the derivative of f of x plus g of x. So when you're adding two things together, you call that a sum. Okay? So look, the derivative of a sum is the sum of each derivative. I'll say that again, okay? The derivative of a sum is just the sum of each derivative. All right? Here's the difference rule. You could copy paste that. The only difference is the minus sign. Right? The derivative of a difference is the difference of each derivative. The derivative of a difference is the difference of each derivative. The derivative of a sum is the sum of each derivative. Okay? Saying it is probably more complicated than actually doing it. So let me show you here. This is called the sum and difference rule. Again, it's not a rule that you have to remember because it's so intuitive. Okay, it's so easy to understand. So here's example, I think this is 3. Okay, it got cut off, but go ahead and put a d over dx right here, okay? Here's the derivative of x to the 8th plus 12x to the 5th minus 4x to the 4th plus 10x cubed minus 6x plus the 5. Okay, looks complicated, but it's not. So basically, when you have a sum or a difference, okay, it's the same thing as just taking the sum and difference of each derivative. So here's what you do. What's the derivative of x to the 8th? That's just 8x to the 7th. Here's a plus sign, I'll bring it down. And then you take the derivative of 12x to the 5th. Pause and play when you're ready. 12 is a constant multiple or a coefficient, so you leave that to the side. X to the 5th is 5x to the 4th. You bring back that 12. That's going to be 60x to the 4th, followed by a minus sign. Okay, now keep going and do the rest. And then play when you're ready. The derivative of 4x to the fourth is going to be 16x cubed plus 30x squared minus, now remember this is linear, 6x, so the slope is 6, okay? 5 is a constant. What's the slope of a constant line? That's a 0. Or you remember that the derivative of any constant is going to come out to 0. So that goes away. So here you have it. All right. It's that easy. It's just everything that's separated by a plus or minus sign, you're just taking the derivative of each. Okay? You know what? Let's do one more. Let me squeeze in one more. And then we'll end it for the day. The derivative of x to the 9 plus 4x to the 6 minus x to the 1/2 power plus the cube root of x minus 1 over x to the 5th power. Okay. Take as much time as you need before you press play again. Okay? All right. So the derivative here is going to be 9x to the 8th plus the derivative here is going to be 24x to the 5th power. This here is going to be minus 1/2 x to the negative 1/2. The cube root of x is the same thing as x to the 1/3, so the derivative of that is going to be 1/3 x to the negative 2/3, because you have to subtract the, the power by 1. And 1 over x to the 5th is the same thing as x to the negative 5th power, so the derivative of that is going to be negative 5x to the negative 6th power. So hopefully you got that. We could definitely clean this up, okay, but I'm not going to. But if at the very least you got that or something equivalent, you guys are on the right page. That's basically it. You guys learned the power rule, okay? You learned that the derivative of any constant is 0 because that's the slope of a horizontal line. You learned that constant multiples, you ignore it, and then you bring it back later. And then you learn about the sum rule and the difference rule, where you just take the sum or difference of each derivative. Okay? A lot of rules, but really out of these 5, they're not really rules. The only rule you have here is maybe that first one, but we proved it. Okay? So hopefully you guys find that that's a little bit more intuitive. Oh, wait, I think I have one more. Wait, hold on. Oh, there's more. I'm sorry. Let's keep going. Example 4. Okay. Find the points on the curve. Y equals x to the 4th minus 6x squared plus 4, where the tangent is horizontal. Okay. Think about what this means here, okay? Okay. So you have this curve. I don't know what that curve looks like. You're trying to find out where the tangent lines are completely horizontal. So I don't know if that's what it looks like, okay? But for instance, this tangent line in purple is not horizontal. This tangent line here is not horizontal. This tangent line here is not horizontal. But this tangent line is horizontal. 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 We're trying to find out where, so points, where the tangent line is horizontal. Think about the context here. A tangent line. So when you think of the word tangent, you should be thinking of the word derivative, right? So what does it mean when the tangent line is horizontal? What does that say about the slope? Okay, you guys should know that a horizontal line has 0 slope. So we're trying to find out where is the derivative 0. Okay, so here we go. We have y equals x to the 4th minus 6x squared plus 4. I'm going to go ahead and find the derivative, so I'll call this y prime equals. Okay, so the derivative here would be 4x cubed minus 12x. And the plus 4, since it's a constant, it goes away to 0. Okay? So this is my slope here, you guys. Okay, I'm trying to find out where the slope comes out to what? I'm trying to find out where the slope comes out to 0, because you want your tangent lines to be 0. So what you do here is you set your y prime equal to 0 now. All right? And then this goes back to a little bit of IM2 and IM3, or even pre-cal. You got to factor this guy. I could take out the GCF of 4x. That'll leave x squared minus 3. And if you use the zero product property here, 4x is equal to 0, x squared minus 3 is equal to 0. X will come out to 0 here. If you add 3 on both sides here, x squared will equal 3. And if you square root, don't forget when you square root, you get a plus and a minus. Since I can't square root 3, I'll just leave it there. Okay, what do these represent, right? These represent all the x coordinates. So I know that this is where the tangent is going to be horizontal at 0, at negative radical 3, and at positive radical 3. But they're looking for points. So a point consists of an x and a y. So what you have to do here, it's a little bit of a plug and chug. You're going to take x and you're going to plug it into the original function. Okay, 0 is easy to plug in. You just get 4. I don't care about what happens with negative rad 3 or positive rad 3, but I'm just going to cheat here. If you plug in negative rad 3, and I would encourage you to just use a calculator because this is just a small part of the problem, okay? You end up getting negative 5 and negative 5. Okay, so these are the 3 points where the tangent line is horizontal. Here's a visual for you guys. This is how the graph actually looks, and this is the moment where the tangent lines are completely horizontal. All right. Let's stop here. Okay. So one last thing, one last thing. So there are some other derivatives that you guys may need to know. I'll send you guys a PDF of the list of derivatives that you guys need to know. There is logic behind it. And if you are curious, I encourage you to just ask me. But I don't want you guys to think of these as rules. It's more of I'll prove it when we have enough information. So when you guys know a little bit more about calculus, that's when I'll be able to kind of uncover why these, I'll call them formulas, are the way that they are, okay? So sometimes you won't run into a power rule where you have some type of x or some type of variable to the some number power. So we know that that derivative is just going to be nx to the n minus 1. Now, what if you don't have some type of power, right? So sometimes you run into different functions. For instance, e to the x, okay? And again, I'll prove this when we have enough information, but the derivative of e to the x, this is probably the most difficult one. The derivative of e to the x is e to the x, the exact same thing, okay? If you didn't catch my sarcasm, you will. So here's another one. Now, why that's true, I'll explain later, okay? The derivative of sine x is cosine x. Again, I'll prove it when we have time, okay? Or when we know enough. The derivative of cosine is negative sine x, okay? There are some other ones, all right? There's one for tangent, there's one for secant, cosecant, and cotangent. okay? I'm not going to go over those now. That doesn't mean that they're not important, okay? But these four are probably the one that occurs the most, so I kind of want to go over that. There's one more. The derivative of the natural log of x is 1 over x, okay? So for now, just try to remember these, look back at it, and then slowly pull away until you don't need it anymore, okay? But I will prove these to you guys when we know enough to actually prove it, okay? What else is there? I think I'm missing something. Oh, okay. This last part, really last part, okay, is just an introduction to something called particle motion. It's huge when you get into the AP exam mode, okay? Particle motion is basically when a particle, when a certain object is moving in a direction, usually left or right or up or down, okay? So some things that you need to know is just this for now, okay? They'll use different notation. So instead of f of x, they'll use s of t, t being time, okay? Now, s is going to represent the position, okay? Now, just a little history lesson. S was normally standing for stratus, which I believe is Greek for where you are, position. So somewhere along the way, it got lost in translation. So some people are wondering, well, why is position not P of T, right? It's just the history of math. So it originated from Greek, and it kind of got translated over. So S of T is the position. It's pretty much where you are, all right? So at the 5-second mark, where are you from where you started? Just stuff like that, okay? Now, what you need to know is when you take the derivative of S of T, you get S prime of T, okay? You're finding the instantaneous rate of change. You're finding the rate at which your position is changing over time. So let me give you a scenario here. So position, let me give you some units for position. For example, let's say miles. Okay, so at the 4th hour, you are at the 45th mile. Okay, that's position. Now, when you take the derivative, you're finding the rate at which your position is changing over time. Let me say that again. You're finding the rate at which your position is changing over time. In this case, I'll use hour. What do we use in real life that represents miles per hour? Right? Some of you may be saying speed. The correct term here is velocity, and those two are similar but not the same, but we'll talk about it. So just know that when you guys take the derivative of position, you're really talking about velocity here. All right? Now, if you take the derivative of your position 2 times, or equivalently, if you take the derivative of velocity, you get v prime, you're finding out how much your velocity is changing over time, miles per hour, how much your speed is changing. Think about it in real life, right? When you're in your car, how do you change your speed? Okay, it's okay if you've never driven a car before, but the way you change your speed is that accelerator. You either accelerate or decelerate, right? Which is the reason why when you take the derivative of velocity, you get acceleration. All right. If you've taken physics, you might have seen this before. Don't worry if you haven't. Again, this is just a brief introduction, okay? So all I want you guys to know is just the order. So the original function is S of t, position. That's all I want you guys to know. When you take the derivative of position, you get velocity. Okay, when you take the derivative of velocity, or if you take the second derivative of position, you get a of t, which is acceleration. So just remember SVA. Come up with some type of, oh gosh, what do you call it? I want to say acronym. Is it acronym? I forget. But anyways, SVA, don't forget that, okay, for particle motion. So just to show you here how it plays out in a problem, and I'll wrap it up with this problem here. Here we go. Write this down. Actually, you know what? Just write down what I highlight. Just so we can kind of shorthand it. You guys have the problem in front of you, so at least just have the green highlight on your paper, okay? Pause and play when you're ready. The equation of motion of a particle is S equals all that, where S is measured in centimeters and T in seconds. So remember, S stands for position, because that makes a lot of sense. Position, okay? They want us to find the acceleration as a function of time. Okay, so if you guys have position, S of t, now I know they didn't write of t, but you could just put it there. If I have position, what do I need to do to get to the acceleration? All right, pause and play when you're ready. So basically what we need to do here is we need to take the derivative twice, okay? So I'm going to go ahead and take the derivative once right now, S prime of t. So remember that that just represents velocity, okay? So the derivative here, go ahead and do this on your own and then press play. The derivative will come out to 6t squared minus 10t plus 3. That plus 4 is a constant, so the derivative of a constant goes away because a horizontal line has a slope of 0, okay? So I don't want the velocity, I actually want the acceleration here. So I'm going to take the derivative one more time of s, or the derivative of v, however much you want to write it, okay? They're all equivalent, but that represents acceleration, all right? You don't have to write all of these out. I like to write it out until it sticks, so it's up to you. So if I take the derivative one more time, the derivative of 6t squared is just 12t. The derivative of negative 10t, that's linear, so the slope is just the coefficient, minus 10. And the derivative of positive 3 is just 0. All right. So we found the acceleration as a function of time. We just did that. And then they follow up with, what is the acceleration after 2 seconds? What do you guys think we need to do here? Pause and play whenever you're ready. So if we want to find the acceleration after 2 seconds, all we have to do is plug in 2. All right, so a of 2 is just going to be 12 times 2 minus the 10. And that's just going to be 24 minus 10, which is 14. Okay, in this case, it'll be centimeters per second. Okay, or if you want to get fancy, centimeters per second squared. Okay. More on the units later, okay? It's not too important right now, but when it is important, I'll talk to you guys more in detail about it, okay? So, position here would have the units just centimeters because you're just talking about a position, okay? Velocity would just be centimeters per second, okay? And if you go one more, acceleration, it'll just be centimeters per second, all right? That's basically it. Okay, more on what that means later when we learn a little bit more about that, okay? That's it. Thanks.